So I found another example I really like. I was just kind of glancing through the problems in Chapter 4. This is review problem number 8 in Chapter 4. And I know it's a little fuzzy. I've got it a little out of focus at this distance. But anyway, this is in the Hibbler text, Chapter 4, review problem 4.8. And I looked at this and I thought, it's actually, they're just wanting you to do the distributed load. But I looked at that, I was like, that's a really good Chapter 5 problem. Let's do that. We haven't done one with cables yet. So if you want to copy it from the book, go ahead and pause it. I'm going to draw it with you. We're just going to work this as an example. I'm going to change what we're looking for, right? Because it's just asking you to compose the distributed load, I think, into a single force. But we're going to work it as an actual pin and cable attached problem. All that to say, if you go look sometimes in some of the other chapters, some of the problems in there, if you're looking for just additional stuff to work through, sometimes you can find additional problems in some of the other chapters. So they're drawing this thing out to be 30 foot. Obviously, I'm scaling that. 30 foot's going to be huge. But anyway, all that to say, if you're looking for additional problems, sometimes you might find good additional problems in previous chapters, but they'll still have things like fixed supports, pins, rollers. This one's got a pulley in it with a cable, right? So you've got this pulley attached up here, and this cable over here makes a 30-degree angle. This cable here, although I've drawn it terribly, is vertical. And you've got a pin over here. It's calling this is point A, B, and C. I don't know why it's labeled it that way, but it did. A is right there in the middle. And they're saying you've got this distributed load. It is a constant rectangular load from C to A. And then you've got a triangular load starting from A going down to 0 at B. So I'm not drawing that very straight, but it's essentially a triangular load going down. Distances here, let's actually put this, the maximum intensity of this distributed load is 800 pounds per foot. 800 pounds per foot. Again, distributed loads will be some amount of force per unit length. In 3 dimensions, sometimes it's force per area, but in 2 dimensions, it's going to be force per unit length. And again, distances are very simple. Point A is right in the middle. They're saying this thing is 30 foot long, so that's 15 feet on either side of point A. I don't think I've quite drawn it to scale, as most of my drawings are not going to be. That's not my intention here. And what are we trying to do? Find tension in the cable AB. It is the same cable. It passes over a pulley. Did they label the pulley? They did not label the pulley. So it's the same cable going from point A all the way around to point B. They want us to find that tension. And they also want us to find and reactions at the pin C. Okay. So how do we find reactions or a tension of a cable or something like that? These are forces. How do we find unknown forces? Newton's laws. How do we apply Newton's laws? Most likely we want a free body diagram. So I'm going to draw a nice simple free body diagram. Doesn't have to be too terribly complicated, nor should it be. But basically we're going to remove the pin, we're going to remove the cables, and we're going to replace it with the appropriate reaction. So again, a pin, it can rotate so there's no reaction moment, but it does have a reaction force in, it either has an X and Y component of reaction force, or it's an unknown C at some unknown angle. You can work it as an unknown magnitude and angle or magnitude and direction. That's fine. I don't. As you guys are picking up, if you've been watching these for a while, I tend to resolve all of my forces, so I personally wouldn't draw this the other way. But if you're perfectly okay and don't mind drawing it as magnitude direction, go for it. It doesn't bother me. We can get to the same place. I'm not going to count anything wrong. I'm not that guy. I've got a tension. So again, I've got the same cable from here to here. cables always pull. They can only provide tension. So as this thing sags or pulls down, it just strikes me that cable's not going to hold any tension. So we're going to have to, let's say, pause just for a second. I'll be right back. Okay, I debated restarting this video and recording it over, fixing my mistake. I didn't. These are not up. If you look at the original problem, I apologize. I'm terrible today. These are going down. I was like, how does this problem work? That cable's not holding any tension. What? No. These are going down. That would make more sense. Yeah, if we push this beam up with this distributed force, then it's just going to push up, right? There's nothing pushing it back down except for a little y direction force here. But if we pull it down, so we're saying, all right, we're going to pull this thing down, and these cables up here are going to basically hold it in place. So I've got cables holding it up. I've got y direction force here also helping hold it up, and then part of this tension is in the x direction, so it's going to get counteracted by this x direction force to keep this thing in place. But basically, we're hanging a bunch of stuff off of this thing. So we've drawn this as a distributed load. Maybe it's some sort of sign, like some sort of sign that's like really heavy right here, and then it gets kind of thinner as it goes up there. So you end up with this distributed load that starts out constant, and then as you get further out, it's lighter and lighter per unit length. And we're just drawing it as distributed load. So I apologize. These are not up arrows; these are downs. So redraw it in your notes if you like. If you're better than I am, when you saw the original problem, you're like, no, Steve, I'm going to draw those up. I'm sorry, I'm going to draw those down like they were supposed to be. Okay, where were we? All right, disaster averted. I didn't redo this video because I wanted you to see it's okay to make mistakes sometimes. But eventually what would happen is we would have gotten to a point where it's like, all right, I've got a negative tension in this cable. That doesn't make sense. And then you go back and say, okay, well, did I actually get everything from the problem correct? And that's literally what I did. I looked back down at the problem and said, oh, no, I drew it incorrect the first time. So I wanted you to see that that's okay to make that kind of mistake. What you want to do is when you get down to a point where you start trying to put numbers to it, or trying to apply logic to it, at some point you need to start thinking like an engineer and think, okay, well, can this physically work? Does this make sense? Am I missing something? Did I not get something? And that happens all the time. You might miss something from your customer, your client, or your manager, or they may have told you something wrong, or you just wrote something down wrong. That happens. So wanted you guys to see that. That's okay. All right. So I've got tension AB. Again, it's this cable up here runs across this pulley and back over here. So it's the same cable all the way through. So it's the same tension in that cable all the way through. Here it's vertical. So I'm removing a cable here. So I need to draw a vertical pull force right there. And then I'm removing a cable down here. It's at an angle. You can draw it TAB here at an angle of 30 degrees. You guys know me. I like to go ahead and resolve it right from the beginning in a free body diagram. TAB sine 30 because it's the vertical component is opposite of the 30 degrees. I'm going to draw TAB cosine 30. Why am I drawing it back there? Well, it's because I can move that force anywhere along its line of action and not change the effect of that force. So I'm going to go ahead and pull it back there, out of the way. And then you can do this as a single force if you like. I'm going to break it into two components. I'm going to say right here, everything over here, this first 15 feet is a constant rectangular load, and then the last 15 feet is a triangular load. So let's focus on this 15-foot rectangular load first. So I'm going to have a single force. If you go back and look at how do I deal with a rectangular force or rectangular distributed load, it's going to turn into a single force applied right at the middle of that rectangle. And it's going to be the area of this rectangle. That's going to be this 800 pounds per foot multiplied by the 15 feet. I'm going to pause because I don't have that number. Mostly wanted to pause so I could get my calculator out and going. I've just got a simple calculator app on my phone that I like because it's real easy to see what I'm doing. And I learned to use a calculator like this when I was in school, not because I didn't have a graphing calculator. I did, and I loved it. But I don't know, I got really good at this. And what I will tell you guys is for the FE exam, getting prepared for that. This is the kind of calculator you would be allowed to use as something you can't enter text into. So if you get used to using one of these, and you can see this is just a free app I'm using on my phone. I'm not going to tell which one. If they want to sponsor me, maybe that's another discussion. But anyway, so we got that. Okay. He is halfway along this 15 foot. So I'm going to put him halfway along that 15 foot. That is 7.5 feet there. Okay. And then it's another 7.5 feet to where that point A is. And now I've got this triangular load here. So it's going to be half of this, because again, it's 800 right here. It's 800 all the way across. Half of the 800 times 15. So it'd be half of this 12,000 pounds. So it's going to be 6,000 pounds. Where do I put it? Well, it's going to be right here in the thickest part of it. Basically, it's the center of the triangle is not halfway in between because it's not equal down here. I've got more weight, so to speak, right here. And remember, we talked about last time, it's 1/3 of the length from this, from the thickest end, or 2/3 of the length from this zero end. Well, so if I go 1/3 of this 15-foot span, 1/3 of 15 is 5. So I'm going to put this 6,000 pound force here. Is my pen trying to die on me? There we go. 6,000 pound force there. And that is a distance from point A. It's 1/3 of that 15 feet, so it's only 5 feet from point A. And then their last 10 feet to get out there to the end of the beam. If it helps, you can dot lines up in here so you can see where those are going to. I've had to move it down a little ways. Okay, one free body diagram. How many unknowns do I have? Well, I've got TAB. It shows up in 3 different places, 3 different terms have TAB in them, but it's all the same unknown. It's only one unknown TAB each time. I've got CX and CY here. Those are both unknowns. So that's 3 unknowns. I can write 3 equations with 3 unknowns. Right? This might be a time where you write a more than one moment equation. I don't know. And you don't have to start with the forces. You can always start with a moment equation. If you look at this and say, hey, Steve, you know what? If I take the moments about C, both CX and CY go away, I'm left with TAB as my only unknown. By the way, I don't have answers to this, so if you're getting different numbers, say so. You guys saw me get the 12,000. I'm pretty confident with that. But if you get other numbers, leave them down there in the comments. So if I take moments about point C, okay, I'm going to start with the counterclockwise ones. That's this TAB right in the middle. So TAB at a distance of 15 feet. And then I've also got TAB out here. So there's 2 different TAB terms. They're both going to apply a positive moment to point C. They're both applying a counterclockwise rotation. So this one's plus TAB sine 30, if memory serves, I think that's a half, times 30 foot. And I'm going to have 2 negative moments here, one here, one there. All right, I think I'm going to run out of room, so I'm going to write them on the second line here. This is all the same equation, just taking up 2 lines. So this 12,000 pounds is causing a counterclockwise or negative rotation. 12,000 pounds, and it is a distance of 7.5 feet from point C. And then I've got 6,000 pounds out here. So it's also it's also clockwise, so also negative 6,000 pounds. And that is a distance of, this is 15 plus 5 makes 20 feet from the edge. Okay. Let's make sure here. So if I take the sine of 30, that is a half. That's what I thought. Make sure your calculator's in the right units. So sine of 30 times 30 is just going to give me 15. So I've got 15 feet times, this is also 15 feet. So I've got basically 2 TAB. Let's write it out here. Skip as much as the algebra as you're comfortable with. 2 TAB times 15 feet. Again, I'm saying that sine 30 times 30 feet is 15 feet. So 2 of those, 1, 2. And that's going to equal, I'm going to move all these negative guys over to the right-hand side, or the other side of the equation, I should say. So they'll pick up a positive sign. So it's going to be 12,000 times the 7.5 foot. And then add to that the 6,000 times 20 foot. So I've got here that is 210,000, and the units there are pound times feet, so it's pound feet. So when I divide by this foot here, I should be left with pounds. So I'm going to divide that by this 2, and I'm going to divide it by the 15. So I'm going to have TAB is 7,000 pounds. Again, you guys can see how I've done that, but I definitely can have easily, I wasn't paying super close attention. I may have done an add or a minus. I was recording thermo videos one time, and I did that. I hit the wrong key on my calculator and came out with the wrong answer, and so I had to pause and go back and find it. So if I made a mistake, say so. Okay, are we done? Is that, what did we need? They wanted, what were we looking for? TAB, found that, and the reactions at C. Trying to find the reactions at C. Okay, good. It is entirely up to you how you want to approach it. I would say I'd say pause it here and go find those other two unknowns. How are you going to find CX and CY? Pause it, go find them, and then let's work through it. In fact, I'm going to pause the video here so this doesn't get too long. Okay, how'd you do? I've got CX here CY here is 7,500 pounds. I just use the sum of forces in the Y direction to find that. I did look at this and thought, hey, you know what? I could take, now that I know TAB, I could take my sum of moments right here, right? And then CY, and then I do have this guy, but I do have, I don't know, I still had 4 terms, taking the moments there. Same thing here. If I took the moments here, I still had 4 terms. So I thought, well, let's just write CY, or write sum of forces in the Y direction. Yeah, it's 5 terms, but I don't have to worry about moment arms that way. Nothing wrong either way, right? In the X direction, about the only way I'm going to get to the CX, because it does pass through all points along here, unless you want to take sum of moments about some arbitrary point out here that CX would cause a moment about, but then that just gets kind of silly. You could, there's nothing wrong with that. Just apply all moments taken to some point. It doesn't even have to be on the body. You can take some point out here in moments, and this would cause a moment out there. It still has to sum to be 0. But that just seemed silly, right? Sum of forces in the X direction, just 2 terms, solve it. Notice I just wrote us a note here. This is 6062 pounds. It's really 6060 would be great. 6062 I wouldn't count wrong. I would count this wrong. It is not this. How do I know that? Because we don't care. Simply put, we don't care. If I'm dealing in thousands of pounds, I'm not going to care about ounces, grams. We're talking about, you could set a cup of water on this thing and that would be equal to this amount. It's just not. When you're dealing in thousands of pounds, we don't care about these decimal places. 3 significant figures, unless you've got a really, really good reason, 3 significant figures. Anyway, questions, comments, and of course units, always try to instill that. If there's no units, then it's wrong, unless it's a unitless quantity. Questions, comments, complaints? Let me know in the notes, in the comments. I think I got this right, but if you're getting something different, say so. And if somebody gets something, you got something different, don't just slaughter them. Anyway, I'm comfortable. That's good for 2-dimensional equilibrium. I don't think I'm going to make any more videos for lecture 9 here. I think for us, we'll probably start unit 3, exam 3. We'll start looking at 3-dimensional equilibrium problems. All right. Have a good one.